So I think we can go on. My topic today is micromovements on implant abutment interfaces, causes and consequences. And this brings us to the first question, why we should have a closer look to the mechanics of implant abutment interfaces. If you ask the implant companies, they always will tell, we've got no problems with the mechanic. We have no screw loosening, perhaps parts per million or something like this. But then is the question why we find in the literature and in some studies these results. We find fractured implant components. We find broken binding screws, loosened binding screws, and perhaps some damaged implants. And we also see that there is a bone loss surrounding the most implants, especially down to the first thread. And the consequences of this could be that we have a problem with our soft tissue. And one cause for this problem with the soft tissue could be the microgap. But the question is, what is the reason for this microgap and why we have some implant systems which has not these problems? So it is not the truth that every two-piece implant lose crestal bone in the first year after prosthetic restoration. We can also see over here, and this is a really interesting picture because only the platform switching is not able to prevent the bone loss. What is the cause for these micro-movements and microgaps? These are the chewing forces, and some measurement of chewing forces shows us that we have a large and high average of approximately 210 newtons. If we chew bread, it's about 100 newtons, and if you chew chili babies, it's more than 250 newtons. It's really interesting. So the chili babies could, in the future, be the killer of our dental implants. There is some elastic deformation and some microgaps. And the question is the screw really the clue? So if we found a better binding screw, we solved the problem? The best way to show this or to explain this problem is if we have a look at the III implant system, an original 4mm implant in comparison to a 5mm implant, and if we compare this both with a platform switched situation, so we have a 5mm implant diameter with a 4mm abutment. And if the screw will really be the clue, the microgap of the 4mm implant should be the same than the platform switched solution because we have the same binding screw with the same initial tension. Now we have a closer look at it, and in the overview we can see that there is a microgap inside of the 5mm implant, and if we have a closer look at it, we can clearly see that there is a microgap and also there's a microgap before, so the manufacturing tolerances in this system are not really perfect. If we compare this with a 4mm implant, it's clearly to see that the microgap increase, and also at the enlargement we can see that there is a really large microgap. But if we compare this with a platform switched solution, we will see that in the overview it's really hard to find the microgap. But if we go to the enlargement, we can see that there is a microgap, but it is really the microgap is really very small. So what is the reason for this? The reason for this are elastic deformation of the implant components, not only inside of the binding screw. So we have a look at the videos again, and please don't have a look to the region where the microgap will occur. Please have a look to the implant wall at the left side. And you will see that there is a really elastic deformation of the implant wall, and this is the reason for the large microgap. In comparison to this, the platform switched situation, and don't have a look to the microgap, please have a look to the implant wall on the right side, and you will see that there is no or only a small elastic deformation. So we can say the screw is only one part of the clue. We should have a look to the whole system. If we have a perfect binding screw and a bad implant, we solved nothing. So we have the chewing forces, and one result are the elastic deformation and the micro movements. But the elastic deformation occurs some shear forces between the implant and the bone, and this we could prove with this Camlog implant system, and we simulate a bone loss of 3 millimeters, and if we load it, you can see the elastic deformation of the implant wall. It's large, and if we simulate no bone loss, it's clearly to see that the elastic deformation decreases. Again, for better understanding, a large elastic deformation and a small elastic deformation. So, if we think about this, the bone, so the surrounding bone, should stabilize the titanium implant. So it's logical that the crestal bone gets really high stress peaks when we load it. So this could also be a reason for the bone loss. But what is a consequence of these micro movements? One consequence is a microgap, and in my opinion, a micro pump effect. So if we have a look at this example, we can see really a large microgap. And if we have a look at the slow motion, you can see that we simulate the side teeth region at the 40-fold slow motion at 200 Newton. We will see that an axial force vector is formed, so the connection moves a little bit down, and when the force vector tilts to the left side, or turns to the left side, the complete interface moves sideways, and the micro gap we will see is in an area of 36 microns. And now think about when this occurs once a day, week by week, day by day, and month by month. What will be the result? The result will be that the inner of the interface will be filled with fluids and bacteria. To prove this, we designed a special gingiva made from a silicon, and we have a special channel for a radio opaque material. And if we have a closer look at it and we start to load it, you can clearly see that the whole fluid will be sucked inside. It's not so good to see with its radio opaque material, so we used a better material, and now it's really easy to see that everything will be sucked inside. And now, ladies and gentlemen, please remember the good old days when you were a little child. Remember those rainy days when you and your friends nothing found thrilling than put on your rubber boots, going outside and jumping from puddle to puddle, until one of these puddles was too deep and all the muddy water comes inside of your rubber boots, and the way home was one squishy step after the other. And it looks a little bit similar what we see here. But you have an advantage. When you were at home, you put off your rubber boots and dry your feet and everything was okay. But your patients cannot remove the abutment every day to dry and clean it. So the result looks perhaps like this. We have really terrible substances at these abutments with a terrible smell. And try it. If you use flat-to-flat interfaces, remove the abutments after 1 year or 2 years and smell the smell. It's really terrible. This will not occur if you use conical interfaces, based on the fact that we have no microgap inside. So if we load it, the AstraTech system, it looks like a virtual one-piece implant. And also the detailed recording could show that there is no microgap inside. And this is based on a good manufacturing tolerances and a good dimension of or design of the conical interface. The same with the Ankylos system, we also see no microgaps inside. But there are some researchers which want to tell us that there is no microgap inside, or we will not see the microgap based on the method. But if we have a look at this BICON system, this BICON interface, we can see below there is a microgap, but the interesting thing is if we load it with 200 newtons, the microgap didn't change. So there is no micro movement inside. And this is a cheap copy of a BICON system, and we can see there is a microgap inside of the interface. And also with this Straumann Synocta components brand new, there are microgaps inside of the conical interface. So if there is a microgap inside, we will see the microgap. Also with the solid abutment, we can see the microgap. So the method will show us if there is a microgap. And if we have good designed solutions, there is no microgap, or we see no microgap because there is no microgap. And also, if we load these Straumann implants, please have a look at this region, to the thread, and here to the conical interface. And you will see that there is a permanent shift, so the occlusion is gone. So the best thing is for you, you will tell your patient he should first chew to the one direction and then to the other, because the occlusion is again in the right position. And also, if we have a closer look to the microgap, we see that there is a gap forming inside of the conical interface. It's logical that we see not such a high contrast in comparison to the flat-to-flat interfaces, but we will see the microgap inside of the conical interface. And if we see no, for example, at the Astrotech system, the logical consequence is that there is no microgap inside. So also, if we see no microgap inside of the conical interfaces, it is logical if we fill it with a radio-opaque material that we will see no micropump effect, because there is no microgap where the radio-opaque fluid can be sucked inside. So for better understanding what is the basic difference between flat-to-flat interfaces and conical interfaces, I have some pictures for you. And the main difference is on flat-to-flat interface that we have a really horizontal bed stop and we have a clearance fit for better fitting. The main difference to the conical interfaces is that we have a conical bed stop, and before fitting we have a clearance fit. And after fitting, we have a press fit if the manufacturing tolerances are really perfect. And the difference from a mechanical perspective is that if we load it with a horizontal component, that the abutment tilts sideways till it will be stabilized inside of the implant. But then it's too late. We've got a microgap. With a conical interface, we have not the problem because we have no microgap inside. If we load it, the forces can be transmitted directly from the abutment to the implant without a high stress for the binding screw. And there is a second reason. We have the effect of conical self-locking. So if you put your abutments inside of the implant, we decrease the microgap, and if we screw on the binding screw, these abutments will be go down inside of the implant, and the implant shoulder will be widened a little bit. The consequence is that this implant shoulder wants to become closer again, so the implant shoulder acts and force out from the implant to the abutment. And normally we should think the force from below will be moved out the abutment, but this will not occur because the cone angles are dimensions that we have high forces from outside and a low force from below. And based on the fact that we have a friction between, there is no problem. We have the effect of conical self-locking. You can test it if you screw in the binding screw at a conical interface and you remove it again, you have a friction between the implant and the abutment. And this is a proof that the manufacturing tolerances are really perfect. So what are the important parameters if we want to design a conical interface? The first one is the cone angle, then the length of the conical surface, the tension of the binding screw, and the manufacturing tolerances. And this should be like a perfect system. If one of these parts are not perfect, the whole system will not work. And we can see this from the bone level implant from Switzerland, and from the first view it looks really very good. But you can see that the conical interface, the conical parts are too small, and if we have a look to the video again and you have a look at this region, you can see we have also a permanent shift inside of this interface. And if we have a look to the detailed recording, we see that it is really a large permanent shift. And we also can see that it starts at only 100 newtons, that we have a gap forming. But the interesting thing is, in the upper region, at our conical interface, we see that the tension is so strong that we have no gap forming inside of the conical interface. But there is a movement inside because it's logical, the abutment tilts permanent sideways. And so we have abrasion inside of this conical interface. And one problem could be we have titanium particles inside and we destroy the titanium oxide surface. So the titanium oxide surface has to be built new, and so we have chemical effects inside near of the bone. And also there is an interesting literature from the orthopedic implantology where we can see that nano and micro particles, which has a size smaller than 10 microns, activates our osteoclasts. So we will get a bone loss. And so we loaded 200,000 cycles and we put it to an SEM analyze, and if we come nearer to it and have a closer look, we see there are really much abrasions inside of this conical interface. And if we have a closer look, we see that it is not only one particle, that are really much particles. And now we change the mode of the SEM and goes a little bit closer to it, and we see it's not one or two, it's 100,000 or million particles, which are smaller than 1 micron. So they can pass the soft tissue without a problem, and I think we will find these particles after some years everywhere in our body. And also, if we come closer, we can see that there are particles which are smaller than 100 nanometers. So we can say that is perfect nanotechnology made from Switzerland. But I don't think that the cells really will love these particles, so we could get a problem with the bone loss. So let's have at least a look for the reasons of crestal bone loss, and we will see that the reasons are not only the micro movements, they could come from the surgeon or from the soft tissue inflammation, and also from the biomechanics, or something we didn't know in the moment, and some thing we know in some years. But if you have a problem with one of these factors, you will get a bone loss. You have to prevent everything. So for preventing the system-based bone loss, you should use an interface which is free from micro movements, free from micro pump effects, and free from abrasions. And if you want to solve such situations which these soft tissue results, you should use a conical interface. The most of the X-ray videos you can download from our website, from the University of Frankfurt, and I thank you for your kind attention.